All right, everybody. So these are parent functions, and we are going to study these parent functions. There's only a couple, I think, that are probably new from Algebra 2, but there's very specific things that you need to know for these parent functions. So let me go through these, and then I'm going to give you the keys of the ordered pairs that you have to know, okay? So we look at this, and we see that this is a line, so linear function. So we can say y equals x, or you can just say y equals mx plus b, which is the form that you're most likely to remember when you're looking at a line. So the points that are super important on this one would be this point 0, 0. And then my slope on this, I would go up 1 over 1, so I would have a point here, or I would go down 1 over 1, and I would have a point here. So we're looking for 3 points. And those would be the 3 points on the line. So if you needed to write out a table, you could, but you really don't need to. So we know we have a line. Okay, we know this one. This is a quadratic, so this is going to be y equals x squared. And let me write the names of these. So this is linear, and this is quadratic. Now, the function is quadratic, but the shape that we have is a parabola. So the points that you have to have on your parabola would again be this vertex. So remember, when we have this point right here is the vertex. And if we went the other direction, this way, this would be the vertex of that point, right? So the vertex is our min or our max of our function. And then if we have a quadratic that looks like this, we're saying that the first point here that we would have would be up 1 over 1 because I don't have a slope. If I had something that looked like y equals 2x squared, this would say that my first point would be up 2 over 1, okay? Now, I don't want you to think of this as slope, because if this was really slope, then the next point would be here, and the next point would be here, and we would have a line, and that's not what we have. What we have is this U-shaped parabola, but when you're looking at points, once you know the vertex, you're just going to go over 1 and up 1 in both directions, okay? This next one is our cubic function. So x cubed, so this is the cubic function. And the points that we have here are again 0, 0, and again 1, 1, and again -1, -1. So if I look at this, it looks again like a line. So just like this one would, it looks like a line. But what we see here is that my cubic function turns. And so because this turns, when we draw this out, we have to have this flattened out part, and then we come back up. So it looks very similar to this kind of a snaky looking look. But the 3 points that we have are the same 3 points that we have in a linear function. So it's important that you just memorize what the shape looks like. Okay? Next one is our absolute value function. And this is the absolute value function. Now, what we really have here are 2 lines. We have this line that goes this direction, and then we have this line that goes this direction. So if I have this point 0, 0, and I have this point 1, 1, and I take the absolute value, that means we can't have any negative y values. So the reason why my line doesn't go down is because my line is going to go up. And that's going to be important here when we deal with absolute value transformations in just a few minutes. So here are my 3 points I've got to have for an absolute value function. Okay, this next one is the square root function. So my square root function, let me write this, square root. I start again with this point 0, 0, and I have this point 1, 1. And then for this function, if you think about it, if I had something like the square root of 4, we know the square root of 4 is 2. So if I look at this, I would have the point 4, 2, which would be this point right here. Okay? I'm not so worried about this point because it's going to change based on the transformation. You have to have these first 2 points so you know which direction your curve is going to go. Okay? So this one's a little bit different because we really only need 2 points. Okay, so here's one. We've done this, but this is going to get more complex now. So we have 1 over x, and this is called a rational function. If you remember, rational is a fraction. That's what we have here. So this is our rational function. Now, there's something that's missing on this function. So in this case, what we have on this function is we have 2 asymptotes. we have one that goes in this direction. And here's why. Because if I have 1 over 0, we say that this doesn't work, right? This is a no-go. So I have this asymptote here, which says that my line approaches 0, but can never be 0 because I know that this doesn't work, okay? And then I also have an asymptote in the horizontal. And the reason for that is because if I have 1 over a number and this equals 0, well, there's no way I can ever make this equal 0. I can't put 0 here because I know that that gives me undefined slope. I can't put a number here because it's going to give me a fraction. So there's no number that I can put in here that's ever going to be 0. So I have 2 asymptotes, and these are required. You have to draw your 2 asymptotes, okay? Now, what's super confusing, and let me just show you this really quick on a calculator. So if I have, let me go in here, and I'll do 1 over x, okay? So if I want to graph this, that's what I see, which is what we have drawn here. But what you'll notice is your calculator doesn't draw the asymptotes. You have to draw the asymptotes, but your calculator is not going to do that. So if you're relying on your calculator, it's not going to be 100% accurate. Okay? So now we have 2 points here that we care about. We care about this point, and this point is going to be 1, 1. And I care about this point. And this point is going to be -1, -1. Now, the value of those points are going to change based on the asymptotes, but what's important is that from this x, I'm going to put an x right here at the origin, that's where my 2 asymptotes meet. So I don't have a point there, I have a little x, and so from this point, from this x, where my 2 asymptotes meet, I'm going to go up 1 over 1. I'm going to go down 1 over 1. And so what I want you to do is think about, okay, after I draw my 2 asymptotes, I'm going to make a little x, and then I'm going to go up 1 over 1, up 1 over 1. And if you look, it's just like this one. They create a line. They create a line. This creates a line. That's why you have to memorize what the functions look like so that you know how to draw it, okay? And we're going to talk more about drawing an rational function here in a little bit when we actually start working on transformations. Okay, this function here is going to be y equals e to the x, and this is our exponential. So e is a special type of function. And so what I could have here is I could have y equals 2 to the x, or y equals -2 to the x. E is a number. E is like pi. It's 2.71 something. And so this letter of E tells us that we're going to have some base, and my base here is E, and I take that to the x power. So that's why it's exponential, because my x is up here in the power. It's not like a cubic where my x is the base. That's the x is my power on an exponential. Now, this is important. On this one, I have 1 asymptote. So my asymptote here is this point right here. And what I have on an exponential is this point from my asymptote, I'm going to go up 1. So this point is 0, 1. And then I'm going to go, same thing with my slope, up 1 over 1. So I'm going to have another point that's going to be over here that's going to be 1 e to the x. Now, this is not what's important. What's important is we see the shape of the curve. So let's talk about the asymptote, because you see it better here than you do up here on the rational function. My curve is going up in this direction, and it's going in this direction. Now, it looks like it just becomes 0, but that's not what happens. What happens is, as I go more and more negative x, which is where I'm going, this direction, this line, this curve, approaches my asymptote. So eventually, if I get way out here, the value that I'm going to have at my x, the y value is going to be like 0.000001. It's going to be super, super close to this asymptote, but it's not going to cross the asymptote out here at the very end. Okay? So, the important thing about asymptote is as you draw this, your line, your curve of your function has to approach that value and get super close. okay? This next one is the inverse. So the opposite of e to the x is going to be ln x. And this is my logarithmic. Logarithmic. Sorry, I think I spelled that wrong. Logarithmic. Now, I could also write this as log some base of x. So when I have a natural log, what I really have is log base e of x. And so ln x is like e. It's a special log, and we call this ln is our natural log. And this is when I have a base of e. So these two things here are related. And I don't know how much you covered with exponentials and logs in Algebra 2, but we're going to have a whole unit on them eventually. Right now we're just looking at the shape and the transformation. Okay, now this one also has one asymptote. This time my asymptote is vertical. Now think about this. If exponential and logarithmic are inverses, so let me just make a little note over here. These two are inverses. It's like multiplication and division, they're opposites. So we would undo an exponential with a log, we would undo a log with an exponential. So they're inverses, they go back and forth. If this is a horizontal asymptote, then it makes sense that my logarithmic is a vertical asymptote. And you can just even see by the shape, they're very similar. So what we have here is one important point, and that's this point right here at 1, 0. And we're going to talk about what that looks like when we get really into functions. But again, you approach your asymptote. That's what this is doing. It's approaching the asymptote, and then it's going off in this direction. It looks very similar to our square root function. See, we have that basic shape that we have here. The difference is the logarithmic can go into the negative, and we have an asymptote that we don't cross. Okay? With this one, I can't have a negative square root. I can't have a negative, or I can't have a square root of negative 2. We know that that's not a real number. Okay? That's why we stop here at 0. Okay, and then we have this last one. So this last one looks a little bit funky. And so what happens here is this is technically a circle. So if you did conics in Algebra 2, what we would have is we would have an equation of a circle. An equation of a circle would be x squared plus y squared equals the radius squared. Okay, and I can look at this one and I can see I go 2 in this direction, 2 in this direction, 2 in this direction. So for this particular example, this is going to be 2 squared, which is 4. Makes sense because the whole thing, 1, 2, 3, 4, all the way across here, my diameter would be 4, which is r squared. But this is not a circle. This is a semicircle. So if I take my equation right here, and I can't plug this in the calculator either to test it, but if I take this equation, I can rewrite it as y squared equals r squared minus x squared. So I move the x squared over, and then if I want the y by itself, I take the square root of everything, and I have the square root of r squared minus x squared. Okay? Now, that is what I have graphed. What I have graphed, let me erase this real quick. What I have graphed is the positive part of a semicircle, positive part of a circle. If you put in your calculator this function, and then you also put in your calculator this function, that's what gets me the other part of my semicircle. That's what gets me this part. Because really, if you remember, when we take the square root of something, we have the positive and the negative. Well, we usually don't write it this way. We would put just the positive in, but if I graph the negative in, that's where I get a circle. So this is a semicircle. Oh, let me stick with my same color. So this is a semicircle because we're only going to graph the positive. So I have y equals the square root of r squared minus x squared. Okay? So what I would tell you, what's most important is that you memorize this page. You know these basic functions, what their names are, what their shapes are, and what the gotta have points are on these. Because we are moving into flipping things around. So I am not going to go through this page with you because this is just the parent functions. And what I want you to do is just use this as practice where you can graph them, you can flip this over, and you can check your answers on the other side. Okay? But I do want to go to the next page, which is this one. So we're going to talk about transformations now. So if I have any of these parent functions, so let's look at this. This tells you f of x equals x, or f of x equals x squared. Okay? So when you see f of x, think about it in terms of, I'm not really truly looking at f of x, I'm looking at just this part. I'm looking at the parent function. So just the x squared, or just the x cubed, or just the absolute value. So when we have this plus or minus c, and it's not connected, so this is not connected to f of x, so I'm adding it on the outside, then this means that my parent function shifts up or down. It shifts up if we're adding, it shifts down if it's negative. And when I say shift, this is a transformation of the parent function. Now this one's different. If you look, this is f of x, and then we're adding on the outside. So when we're adding on the outside, this goes to our b value. So our y value, okay? When this is on the inside, this goes to the x value. It's on the inside. So what happens is we're going to move to the right or left. And again, this is a shift. All we're doing is we're taking it, we're moving it left, or we're moving it right. Now, the important takeaway is because it's on the inside of the parentheses, this is opposite of what you think. All right. This is on the outside of my function. And when I say outside of the function, this is on the inside of the function, right? So this is on the outside of the function. So this is the same as saying I have a negative y value. So if I have a negative y value, let's look at this. I'm just going to draw this. So if I have some function and it looks like this, these are all positive y values. So my function here is y equals x squared. Well, now if I put a negative out here, let me change my color. If I have y equals negative x squared, this is on the outside. So this is going to make all negative values. So this, which has all positive, it just flips and becomes this. Okay, so when we have this negative y, what we're going to say is that this reflects, and reflects is just a fancy word for saying flip. So it's going to flip over the x-axis. So here's my x-axis. My values are going to go from positive to negative or negative to positive. Okay, this is on the inside. So this is negative x. So what happens here is that if I had negative values on the x, they're now going to be positive. If I had positive values on the x, they're now going to be negative. So we say that this reflects over the y-axis. So any values I would have here would flip over here. So let's practice this. I'm going to use these 4 rules and our parent functions, and we're going to practice this. So what I would tell you, the smartest thing to do is identify the parent function, and I am going to just lightly sketch what the parent function looks like. So my parent function here is x squared. X squared is a parabola, so I know I have a point at 0, 0, I have a point at 1, 1, and I have a point at negative 1, negative 1. So this is what my parent function would look like. Okay, but what this tells me is that this negative 4 is out here on the end, so the whole thing is going to go down 4. So there's no change in x because there's nothing happening to the x. If I look over here, I have something on the inside of the parentheses, so something's changing with the x, but this one's not. So all I'm going to do is go down 4, 1, 2, 3, 4. So this is my new starting point. And I know my parent function says I'm going to go up 1 in both of these, and it's going to be a curved shape. So this pink right here is what my new function looks like. Okay, let's go to the next one. So this is a square root function. So my square root function, I start here at 0, 0, and I have a point here. Oops, sorry, my dog's going crazy. I have a point right here at 1, 1. So my parent function is going to look like this. Okay? So now let's go back up here. This is inside my parent function. If my parent function is just x, this plus 2 is on the inside of my parent function. This is on the outside, right? So it's super important to identify if it's on the inside or the outside. So when it's on the inside, this is what I have, which means I'm going to shift to the right or the left. It's going to move right or left, but it's opposite of what I think. So this is going to move 2 to the left. So 2 to the left. We would think 2 plus 2 would move to the right, but it's opposite of what we think. So I'm going to move 2 to the left. There's nothing on the outside that tells me I'm going up or down. So I go back to my parent function, which is 1 point up, and it's going to look like this. This is what my shifted, transformed transformed function looks like. Okay, let's keep going. This is going to be an x cubed function. This is my parent function, is x cubed. So I start at 0, 0. I have a point at 1, 1. I have a point at -1, -1. So it looks like this. And it's super important that this part of the function that you have here kind of flattens out. In fact, hold on. Let me draw this slower so you can see how this is going to look. So I come up. At this point, it flattens out, like it literally flattens out, and then it comes back up. So I have something that looks similar to this, okay? Now, I have two things going on. I have this on the inside, which tells me that I'm going to go right by 2, and I have this on the outside, which means I'm going to go down by 1. So I'm going to go right by 2, and I'm going to go down by 1. So I start at my middle point right here, which is my 0, 0. I'm going to go right 2 and down 1. So this becomes my new point. So this point that was in the middle is this point that's right here now. And nothing else changes. I'm going to go up 1 here. I'm going to go down 1 here. So now I'm going to draw this curve. So it's going to go this way. It's going to flatten out, and then it's going to come up. Okay. Let's get to this guy, because this one is much more challenging. So what we know is I have an asymptote in this direction, and I have an asymptote in this direction. This is my inverse function, so I have a point here, and I have a point here, and I would have something that goes this way, and I would have something that goes this way. Okay? But I have two things happening. So the first thing that I want to do is find my new asymptote. If you remember, I told you we're going to put a little x right here in the middle. That's where my two asymptotes cross. Well, these values tell you where your new asymptote is. So this is telling me I'm going to go up 3, and I'm going to go right by 4. So I'm going to put a little x right here. That is where my new asymptote is. I go up 3, and I'm going to go right 4, opposite of what we think. So I'm going to add my asymptote here, and I'm going to add my asymptote here. Okay, now from the asymptote, if you remember on our parent function, we went up 1 over 1. So here I'm going to go down 1 over 1. So my 2 points are going to be this point and this point. Okay, now when I draw my asymptotes, I'm approaching this line and I'm approaching this line. So what it looks like here is something that looks like this. All right, this is not what I have. So if I have this, it's not this. It's not a right angle, right? If I'm drawing this, it's going to approach that value. It's going to approach this value. It's going to be very curvy, right? It's not going to cross my asymptotes. And I didn't draw them because I was assuming here. So if I have, these are my two asymptotes, I'm going to approach those two. It's also not this. Yeah, the shape kind of looks the same, but I'm not approaching the asymptote. Here I'm going away from the asymptotes. So it's super important that when you draw your curve, it looks like this purple curve right here. I'm approaching these two values. Okay, let's look at this next one. So with this next one, what I have is my parent function tells me that I have an asymptote right here, and I have this point that goes right here. And my graph would look like this. Now, this is my e to the x. The reason why my asymptote happens right here at 0 is because there's nothing here. It's almost like plus 0, right? So I have nothing here, and that's why my asymptote happens at 0. So when I have this -5, this tells me that my asymptote happens, so this value right here, hold on, this value right here is my new asymptote. So I'm going to go down 5. 1, 2, 3, 4, 5. So if I go down 5, this is where my new asymptote takes place. Okay. Now, with a rational function, we needed the x value and we needed the y value. So let me step back for a minute. Here we said the asymptote goes down 5. We went down 5. Here we went up 3. So if we think about this, we went up 3, and this is my horizontal asymptote. So whatever is hanging out here on the end tells you where your asymptote is going to be for your horizontal. So this part is my horizontal asymptote, and this part is my horizontal asymptote. Well, e to the x does not have a vertical asymptote, so we don't have one that goes up and down. This one does, and so this one happens at 4, and that's where this came from. So that's kind of how the asymptotes are related. Okay, so now what we're going to do is we have this x plus 3. So what happens when we have this x plus 3 is that I go from my asymptote. If you think about my parent function, I went from the center of my asymptote, right, at 0, 0, and I went up 1. So there's nothing added or subtracted, so we are starting at 0, and we go up 1. This tells me that from my asymptote, I have to shift 3 to the left. So I'm going to go 3 to the left, and this is my starting point, so I have to go up 1. So this is my starting point. Let me go through this one more time. This says shift left 3. There's no shift on this one. That's why I start right here on the y-axis. So I shift left 3, and then I'm moving up 1 from my asymptote. I approach my asymptote, and then I grow this way. So this value again is going to approach my asymptote. Okay, so ln. So we know that the ln x function, let me draw my parent function. This means that I have this guy that goes right here. I have this point at 0, 1. I approach my asymptote, and I go away this direction. So what happens here is this tells me that I'm going to reflect over the y-axis. So remember, it's on the inside. So if I reflect over the y-axis, that means that my graph is going to be on this side of my x-axis. And this part, plus 2, tells me that I'm shifting up or down. So in my normal parent function, this is my starting point. It's 0 because I have nothing here. But now I'm going to shift up 2. And because I'm reflecting over the x-axis, my starting point actually becomes right here. So if I was just reflecting and I didn't have this plus 2, then my graph would look just like this, but on this side. So it would be shaped like this. But because I have this plus 2, I have to start up here. So again, I'm going to approach on this direction, and then I'm going to go out on that direction. Okay, this one's a little more tricky because we've got this reflection. Reflection sometimes can jam you up. All right, so what is this? This is mx plus b. So we have no change here. We don't have to worry about anything else, so we know we're going to start down 4. My slope tells me I'm going to go up 3, 1, 2, 3, and over 1. Now, I don't need multiple points, but the more points you have, the better your line's going to look, right? So here's what I have. Now, we would never think of this as a transformation, but my parent function is this, up 1 over 1. So this penciled mark right here is my parent function. What I've done is I've started 4 down, so I go down 4, and then this tells me that I have this stretch in 3, so I'm going to go up 3 and over 1. Okay, absolute value function. So this is my absolute value function of x, which looks like this. So I start at 0, 0, and I'm going to go here, and I'm going to make a very defined V. It's very defined. It's not a parabola. So you have to make sure that your parabola, your quadratic, is a U, and your absolute value is a V. All right, so I have a bunch of things happening. So this point right here is not a vertex, but it is a vertex because it's where my two lines meet. So here's my vertex. That's what I'm going to call it. And now what happens is this is going to shift to the right by 2. So if I look at this, this is going to go right by 2. And this tells me I'm going to go up by 1. So if I go right by 2 and up by 1, this is my new vertex. Now, it would look the same. I would go up 1 over 1, but I have this negative that's out front. Now, we know that the negative tells us that we're going to flip over the x-axis. So now this goes negative. So my graph is going to look like this. That's going to be my transform function. And if you think about, we know that when we've had this negative before, that means that it shifts, or that the graph points down. And we've seen this before. So if I have negative x squared, we know that this is a parabola that's going to go down. If I have negative absolute value of x, then I know that this is going to be something that goes down. So when we look at just the parent function and we make this negative, we know that means that it's going to just face down. But really what has happened, if we talk about in a transformation speak, what's happened is this whole thing has reflected, so my positive values now become negative y values. Okay, last one. So with this last one, hopefully you recognize this as a semicircle. So what I have here is that y equals the square root of r squared minus x squared. Well, if this is r squared, then that means that this value here is going to be 3 squared. So this tells me my radius. So I'm going to go 3 in this direction, and I have a point here. And I'm going to go 3 in this direction, and I have a point here. And I'm going to go 3 in this direction, and I'm going to have a point here. And now I have the 3 points that make my semicircle. And so I'm going to make a semicircle here. And what's important, oof, that was not very good. But what's important is that it does not look like a parabola. This is different. So this parabola is going to get wider as it goes, and it's going to be more narrow at the top. This needs to look like, and I didn't do a very good job here, but this needs to look like a full circle. So it's a little flatter on the top than your parabola would be. Okay. I am going to stop there, and I'm going to do another video for just absolute value transformations because those are a lot harder.